Hello and welcome to episode number 18 of CS350 Online. And I'm your host as always, Leslie Eistedt. On today's episode, we're actually going to continue our discussion of devices, and in particular, we're going to take a deeper look at how hard drives work and how to compute the costs associated with doing reads and writes on hard drives. And then we're going to spend some time and compare that to how an SSD works, so you can see just exactly why SSDs are so much faster than mechanical drives. But first, let's look at our OS of the day. So today's OS is called Minix. And Minix was released in 1987 by a gentleman by the name of Andrew Tenenbaum, who is a well-known operating systems researcher and author of several textbooks. And Minix it stands for mini Unix, because this is another one of those Unix-like operating systems. But separate from Unix, instead of being a monolithic kernel, it's actually a microkernel. And again, remember that a microkernel means we're putting the bare minimum of functionality into the kernel, and we try to push everything into a user process if possible. So the original version of Minix, which was written in C, was actually only 12,000 lines for the kernel, the file system, and the memory manager. And if you think about it, that's actually really impressive, because if we look at OS 161, it's bigger than that. In fact, it's twice that big. Now, admittedly, OS 161 has a few other features, but that wouldn't add up to that many lines. Now, one of the other interesting things that they tried to develop with Minix is this concept of self-healing. Now, this is something which has propagated out into other operating systems to various levels of success. But many of you, as I'm sure, have been playing some kind of video game, and while you're playing the game, you get a blue screen of death. And the blue screen of death is almost always because your NVIDIA or your Radeon drivers have crashed. And you get the blue screen of death because when a driver crashes, the operating system doesn't know what to do, and it typically actually brings the whole house down. Minix didn't want the whole house to be brought down when a device driver crashed. What they wanted to do was they wanted to be able to save the program that was running at the point of the crash, not do a blue screen of death, have the operating system detect the driver crashing, restart the driver on its own, and then go back to where the process was at the point of the crash happening. So they wanted to be able to recover from device drivers crashing to make the operating system a little bit more reliable. That's a really great idea, and I don't really know how successful Minix was in this. I can't imagine they had a 100% success rate. Linux and Mac OS and Windows have tried this, and again, to varying levels of success. I feel like Linux handles it reasonably well because you can do restarts of drivers, because you can unload and load kernel modules quite easily. But saying that your game will be saved at the state where that happened, I don't know if that happens so much. Admittedly, I haven't actually played a game in Linux in a very long time. And even then, the last game I played in Linux was Warcraft 3, so it was a while ago. Now, Windows, on the other hand, I know that they are also trying to do this same self-healing. It works better than it used to, but it's still far from perfect. Now, an interesting thing about Minix is it actually was one of the inspirations for the Linux operating system. And in fact, Linus Torvalds, who created the Linux operating system, was actually using Minix while he was creating Linux. And this actually has led to a few lawsuits out there under the claims that Linux has stolen a bunch of code from Minix. But as far as I know, these are unsubstantiated claims because the architecture and the code is different between the two operating systems. I mean, off the top of my head, one of them is a microkernel and the other one's a monolithic. So there's going to be a fair bit of difference between the architecture of these two operating systems. All right. So where did we leave off? So in our last episode, we left off, let's just go back here, and we introduced the topic of devices, which are how we're going to do input and output on our computers, because if you have an operating system, you actually need to be able to start up a program. And if you want to be able to start up a program, then you need some way of telling the computer, hey, start the program. So you need some kind of input device. So devices are typically thought of as input or output devices, but there's also lots of devices in your computer that you cannot see. That can be both, or may just be interesting things like a clock. So those are all devices, and the operating system has to be able to tell them what to do, but also be able to read the status of those devices to learn what key was pressed and so on and so forth. And one of the things we talked about is, how do you actually tell a device to do something or learn about what a device is doing? And what ends up happening, remember, is that the devices themselves have a little bit of computational ability on board. And with that comes their own registers, which we refer to as device registers. Now, these device registers take three different primary types. There's status registers, which tell you something about the device. There's command registers, which by writing, we are telling the device to do something, and data registers, which we use to actually transfer larger blocks of data to and from the device. And of course, you can have combinations of these. So you can have a status and command register, and you can have a command and data register. And we showed you some different specs for such the clock device in OS 161 and things like that. Then we started talking about, well, if those are the devices registers that we have, how does the operating system actually communicate with the device? What is the driver? We showed you a polling device driver, where the driver is responsible for repeatedly asking the device, are you done yet? Are you done yet? Are you done yet? Before we can release the semaphore. And the reason why we have a semaphore for the device is most of these devices are only single access, so you can only do one thing on them at a time. And so the synchronization should be implemented at a kernel level, because it's the user's kernel threads, or the user's threads, that are actually tend to be interacting with the device. So we want to offer synchronization inside the kernel. A lot of devices don't have synchronization of their own. So we're going to use semaphores, and we'll come back to that today as to why we've chosen to use a semaphore as opposed to a lock. But needless to say, there is a reason. The only problem, of course, with the polling one is that that's busy wait. And most devices, not all, will throw interrupts. And so we can take advantage of interrupts and make a device driver that is a two-part, where we have one that instantiates the work with the device, and the second part is actually going to respond to the device being completed. So this using interrupts to avoid polling is used by many devices today, with the exception of USB, which is kind of interesting. USB still uses polling. But then we got into this discussion of, okay, so how do you even talk to these device registers? How are we actually going to send data to these registers on the physical devices? And we talked about port mapped I/O, which, if you recall, that is separate instructions and a separate address space. And then there's memory mapped I/O, where we map each of the device registers to just a place in regular physical memory. And those devices are going to be connected to the main address bus so that they're going to be listening. So we talked about the, the pros and cons of each of those. And then we talked about, for larger data transfers, how we can use program controlled I/O, which is the CPU performs the transfer, or you can use direct memory access, where the CPU tells the device what it needs to copy, and then the device does the copy itself, so that the CPU is actually free to do other work. And I want to give you just a word of warning right now. We talk at a very high level about these kind of hard architectural concepts, especially DMA. And if you actually do any reading into DMA, you'll realize that it in itself is a device, and it's quite a sophisticated thing. Don't worry about going too deep. It's just the higher level concept that we want. Then we concluded our last episode talking about persistent storage as storage that we are going to keep the data after we have lost power. And I showed you a couple videos that demonstrated how floppy drives work and how hard disks work. But just to briefly review that, we have a hard drive, a mechanical drive, and if you were to open it up, and please don't open it up, this is not a safe thing to do, especially if you want the drive to keep working afterwards. But what you would see on the inside of the disk is you would have a spindle, and on the spindle you would have a number of platters. And those platters, while we like to think of them as being made out of metal or plastic, they're actually made out of glass or porcelain, and they're covered in a ferromagnetic material. And it's the orientation of the magnetic field that encodes either a 1 or a 0. And then sitting above each of those platters, but not touching the platters, you have a read-write head attached to an arm, and that read-write head also moves as well as the platters rotating, and that read-write head is actually going to be able to detect the magnetic field underneath of it. Now, one thing to keep in mind is that each of those platters is going to have their own read-write head, and if you have double-sided platters, which means that you can store data on the top and the bottom of the platter, then you would have a read-write head for the top of the platter and the bottom of the platter. And by the way, if that read-write head actually crashes into the disk and actually comes into contact with the platter, that's actually called a head crash, and it's a very, very bad thing. When you have a head crash where the head crashes into the platter, it can damage the surface of the platter such that you can never recover the data, and it can just damage the disk in general. And what's interesting about a head crash is you can hear it. So just for fun, here's a head crash. For one specific, this is a head crash on a Toshiba disk. Each disk has their own unique head crash sound. So that head crash there is actually one that's quite quiet. That head crash was a clicking sound. So if you hear a disk making a clicking sound, get your data off because the head is crashing. Other disks make thunk sounds. Other disks, they just sound like death. There's actually a website out there where you can go to, and they've actually got the head crash and failure sounds for pretty much every make and manufacturer. And it's kind of fun to listen to if you're super bored. All right, so what's really interesting about these mechanical drives, before we actually talk about the costs associated with them, is that they are incredibly fragile. So you have this head sitting at just microns above the platter, and it can't touch down. And then the platters themselves, they're spinning at a really rapid rate, and they're made out of fragile materials. So if you want to know why people have been making a move away from these into SSDs, I mean, there's two reasons. Number one is a performance, as you'll see. But the other reason is that these disks are really, really fragile. You have multiple motorized components. You've got glass, very, very high moving things, very, very fragile in general. So, I mean, we don't tend to use them in laptops anymore because when you're moving a laptop around all the time, you're going to increase the probability that you actually do damage to one of these mechanical drives. Now, I have a really fun video for you, and this is actually off of YouTube. It's from an Open Solaris data center. And I usually show this in class, but it's a really interesting video. And I want to show you just how fragile these disks actually are. So what you're going to see in the video is they're in a data center and they've got this big unit of hard drives, and they're going to show you how doing a certain action, which please don't do on your co-op terms once you return to co-op terms in person because your boss will fire you. But this certain action that they're going to do is going to have an impact on the performance of the disks. And it seems like such an innocent thing, but while you're watching this, keep in mind that these are mechanically moving objects. They are spinning at very, very high speeds. So without further ado, I give you
Hi, I'm Brendan. We're here in the Fishworks lab. Sorry for screaming, it's very loud in here with the air conditioners and servers all around me. We just made an interesting discovery and we thought we'd show you straight away. So over here I'm measuring disk I/O operations broken down by latency. I've also drilled down to disk I/O operations taking at least 520 milliseconds broken down by disk. This is using dtrace so I can do performance analysis of disks. I'm applying a write workload to 2 JBODs, which are over here. The lights are blinking on these JBODs because they're doing work. What I'm going to do is not recommended. This is not supported. Do not try this at home. Ah! This is not special effects, this is real. What we're looking at here is the effect of disk vibration.
So that's a real fun video, isn't it? What you should have seen in there is each time he yelled at the disk arrays, there was a giant spike in the number of operations that took more than 500 milliseconds to complete. What that's illustrating is that those additional sound waves, and I know that was a very noisy room, but it's a kind of a uniform white noise, that additional waveform was sufficient to alter the motion of those high-speed moving disks and affect the latency of the job operations. These disks are incredibly fragile. And it's one of the many reasons why we've been moving away from them recently. Now, as I said, there's a lot of moving parts in here. But how is the data actually laid out on the disk? So if you actually were to take a look at a platter, you would see, and I mean, we can't see this with the human eye, but a platter is actually divided into these concentric rings called tracks. And we call, if you take the same track for each of the platters, we call that a cylinder. So each of the tracks, what we're going to do is we're actually going to subdivide them like a pizza. So this is actually a pretty bad example here because the numbers are kind of haphazardly spread around the world. But if I open up my notebook here and wait for my tablet to connect, what we can see, just a new page, is we've got our platter, and there's our tracks, and then what we're going to do is each of those tracks is subdivided into a bunch of sectors. So this is a sector, and this is a sector, and this is a sector. So we've subdivided each track into a sector. Now, for simplicity's sake, we're going to say that every track has the same capacity. We're also going to say that every sector has the same capacity. And a very common sector size on most disks is actually 512 bytes. All right. So we've physically laid out data onto this track. And then what we have is you have the read-write head. And it is going to need, in order to read or write data in a sector, we're going to need to do 2 things. The first thing that we're going to need to do is rotate the platter so that the correct sector is underneath the read-write head. The second thing that we're going to need to do to even start our read or write is we're going to have to move the read-write head so it's sitting over the correct track. So the platter is rotating and the read-write head is moving back and forth. That's the seek operation. Once you have your read-write head positioned correctly over the first bit, it doesn't read the whole sector. It can only read like 1 bit at a time. Once you have it positioned over the first bit, then the platter has to keep spinning so that the read-write head can read the entire sector. So all of the operations from rotating to get the correct sector, to seeking to the correct track, to the actual read operation, all of those actually involve mechanical motion of the drive. And you can imagine that if you actually have to physically move something, it's not free. I mean, moving electrons isn't free either, but moving things physically to the human eye is definitely not free. So when we're talking about doing an I/O operation on a physical drive, we are talking about the cost model. What is the request service time? That is, how long does it take to find the correct thing, but also do the transfer of that thing? And this request service time can be broken down into 3 separate costs. We have the seek time, which is how long it takes to move the read-write head to the correct track. Now, the minimum seek distance is going to be 0, and that would simply imply that we are already over the correct track. And if we were reading data that was stored sequentially on the disk, we would already be on the correct track. The maximum seek time is going to be, of course, the time it takes to go from the innermost track of the disk to the outermost track on the disk. And interestingly enough, seek time is actually the dominating cost for the request service time. And when we're trying to minimize the costs, we're usually trying to minimize the seek time. One of the other costs is the rotational latency. So how long does it take until the desired sector spins under the read-write head? Now, you might think of your hard drive as being parked until you ask for an I/O operation, but it isn't. An interesting thing about hard drives is that the platter is always spinning. The reason for this is it takes a little extra energy and a little extra time to get that motor up and running. And I mean, if you've ever booted a computer with a mechanical drive and listened, you can actually hear the drive spinning up. Given how often I/O operations happen on modern operating systems, it doesn't make sense to be constantly spinning up and down the disk. So our platters are actually constantly spinning. So with rotational latency, we're estimating how long does it take until our desired sector is actually under the read-write head. Now, this is computed as a fraction or as an amount of the rotational speed of the disk. So we give the speed of the disk in terms of rotations per minute. And the minimum can be 0, and the maximum amount of rotational latency would be the cost it takes to spin the disk exactly once. The last part of this cost is the transfer time. So once you have that first bit aligned with the read-write head, you're going to be either reading or writing some number of sectors. Now, here's something interesting about disks. We like to think of data as being bit or byte addressable. We can only do byte-based addressing in physical memory, so RAM, but on a disk, we don't do byte-based addressing. We actually do sector-based addressing. That is the smallest level of granularity we get. So if you want to read 1 byte in the middle of a sector, you actually have to read the entire sector. And the same with a write. If you want to write 1 byte in the middle of a sector, we're going to have to actually write the whole sector, because the disk does not address things inside of the sector itself, and it can't move to a partial sector address. So our transfer time, whenever we are reading or writing, assumes that we are in the correct position already, and we are simply calculating what is the cost to rotate the platter through however many sectors we are doing as part of this read or write. Now, we don't differentiate between the costs of read and write because they're kind of negligible, but we are going to need to compute how many sectors am I going to read. And it's going to give us a fraction of the amount of time it takes to spin the disk around exactly once. And in order to compute that, of course, then we need to know how many sectors per track and so on. So then our total service request time is the sum of these three costs. So it's the sum of the seek time plus the rotational latency plus the transfer time. Now, people always ask me, why do we add seek time to rotational latency? Can't we be rotating the disk while we are moving the read-write head? And the answer is, well, they are moving. But once the platter gets to the correct start position, it doesn't stop moving, which means that by the time the read-write head has moved into position, the platter may have moved the sector out of position. So it is considered a sum of the costs. They don't happen at the same time. Now, obviously, associated with the service request time, there's a bunch of things we need to be able to calculate. So we have this little example here that I'll walk you through. So let's suppose we have a disk and the disk's total capacity is 2 to the power of 32 bytes. We're going to assume that our disk has a single platter, and it's a single-sided platter, and there are 2 to the power of 20 tracks. We're also going to assume that each track has 2 to the power of 8 sectors. And we've given you the speed of the disks as 10,000 RPM, and we've also given you the maximum seek time. Remember that maximum seek time is the time it takes to go from the innermost track to the outermost track. All right. Now, a lot of this information will be provided to you by the manufacturer. Now we need to be able to compute the service request time. So there's a bunch of things that we need to work out. First off, it would be interesting to know how many bytes exist per track. Well, this is a fairly easy computation. You're going to take the capacity of the disk. In this case, it's the disk capacity. But if we were talking about a system where there were multiple platters, then we would have to work in, well, how many platters are there? And then we'd have to do a slightly different calculation. And those formulas are actually posted to Piazza on the disk drive guide. So assuming we have a single platter, single-sided disk, then we take the disk capacity and we divide it by the number of tracks, and that will tell us how many bytes are there per track. Once we know how many bytes there are per track, we can compute how many bytes there are per sector. So then we take the bytes per track and we divide it by the number of sectors per track. To compute the maximum rotational latency, we're going to we compute the max as 60 divided by the number of revolutions per minute. If you're not sure how I arrived at this particular formula, take a look and try to figure out if I can do 10,000 revolutions per 1 minute, how many revolutions can I do per 1 second? So you end up with 10,000 over 60 is equal to x over 1. And I'll let you figure out the math from there. Now, that's when we have the maximum rotational latency and the maximum seek time, we can do two things from there. We can compute the actual amount of time that it takes to go from track A to track B or sector A to sector B. But in order to do that, we actually need to know at what start track were we on and exactly how many tracks over are we moving. So if you want to know what is the actual cost per moving an individual track, then you would take the maximum seek time and you divide it by the number of tracks, and that will tell you how much it takes to move a single track. And then if you need to know how long it takes to move 10 tracks, you simply multiply the cost of moving one track by 10. And we can do the same thing with sectors. So the cost to transfer a single or move a single sector is the maximum latency divided by the number of sectors per track. And then if you have to transfer or move multiple sectors, you multiply that by the number that you need to move. Most of the time when we have a disk I/O operation, though, we don't know the specifics of our starting and ending track, and we don't know the specifics of our starting and ending sector. So instead, what we have a tendency of using is the average seek and the average latency. And we could go over the expected values and so on and so forth, and this has been changing over time, but for now you can make the assumption and you don't need to prove this because this is not a course on proofs, that maximum seek time is average seek time is the max seek over 2, and average latency is roughly max latency over 2. You don't need to worry about how we arrived at that. It's a big expected values computation. You can just take it for granted. And then what we want to compute at the end is what is the expected cost to read 10 consecutive sectors from this disk. So I want to know what is the request service time for reading 10 sectors. Now, if we go on to the next slide here, you can see all the computations, and you can see here how we have done this as we got our average seek time as 10 milliseconds. Because we don't know what our start and ending track was, we got our average rotational latency as 3 milliseconds because we don't know our start and end times. And then our transfer time is 10, because we are transferring 10 consecutive sectors from the same track, it's 10 times the cost to rotate through a single sector. So 10 times 0.0195 milliseconds. And when you add them all up, you get the total amount of time it takes to perform this operation, so 13.195 milliseconds. That's noticeable, by the way. That adds up. These operations are not free. That was a single read or write. Single. Costly. All right. So a couple things to point out then. One of them is that if every time we do an I/O operation, it's on a different track, or the sectors are not consecutive, you can imagine that the cost of those operations would be very expensive compared to doing a bunch of single reads where they're all on the same track. What we're saying is that random I/O is significantly slower than sequential I/O. So from a disk performance perspective, it makes sense to store your files sequentially on the disk, so that if you're reading a movie or watching a movie, you do the seek operation once and then you just spiral outward. So you're minimizing the seek time and you're minimizing the rotational latencies. Unfortunately, that's not how we save files on disk. Great idea for performance, but in practice that doesn't actually work because we end up with fragmentation issues on the disk, which we will discuss in the next section of the course. So we want long sequential I/O operations, but in reality, we don't have long sequential operations. Now, we have observed that these operations, it's not so much the rotational latency that we're worried about, it's that seek time. Now, historically, if we're looking at things, your highest end drives today can have a maximum seek time around 4 milliseconds, which is really, really great. But consumer grade drives usually have maximum seek times which are significantly higher than the high-end drives. So if you were to go and buy a disk off the shelf today, you can anticipate that the maximum seek time is somewhere between 9 and 12 milliseconds. So sequential I/O is really important. Now, given that we know that sequential I/O is not really what happens, we have to ask ourselves, is there any other way that we could minimize the cost of doing random I/O? And the answer is actually to schedule our read operations. So the idea here is we know that our files are not stored sequentially on disk. And we'll go over that again when we talk about file systems. But what we want to do instead is, since we know they're not sequential, can we rearrange our I/O operations in such a way that we are minimizing the amount of travel that our read-write head does? We want to overall minimize seek time on average. So given a queue of I/O jobs, can we reorganize them to minimize that cost? Now, you might be wondering, who performs the scheduling of these I/O jobs? The answer isn't a definite one. So it can be the kernel. The kernel can definitely do scheduling. The drive can also do its own scheduling. But you can also have both. So you can have the kernel and the drive both performing this scheduling. And they may even use different algorithms, which is kind of an interesting quirk of drives. So the most obvious thing that we want to make sure, so there's two kind of goals we have here. Number one, we want to minimize the seek time on average. So we want to minimize the amount of travel the head is going through. And number two, we want to make sure that no jobs starve. Because a job starving for a disk I/O operation, think of that as you open a file, but it never actually opens. You'd be angry. Well, that's what would happen if one of these I/O operations fail. So we don't want any starvation, and we want to minimize the time. Well, we know a very easy algorithm. It may not be optimal, but we know that it doesn't starve anything, and it's very fair and simple, and that's first come, first serve. So if you look at this diagram at the bottom of the slide, you'll see this black square, which is our read-write head's current position. These concentric rings are the tracks on the disk, and the colored dots represent the locations of the different jobs on the disk. Now, the arrival order at the bottom, which you may not be able to read, is 104, 183, 37, 122, 14, 130, 65, 70. So that's the order that the jobs arrived, and first come, first serve. What we're going to do is simply serve those jobs in the order which they arrived. And these black arrows here will actually show you that we start here at about track 52, then we go to track 104, 183, back to 37. So you can actually track the head movement here. And you see that we're moving the head around a lot. So first come, first served, easy to implement. It's fair, but it doesn't actually optimize anything. So are there any other algorithms that we could use to minimize our seek time? Well, one of them is the shortest seek time first. And this is kind of a greedy algorithm, and it's very much related to the scheduling algorithms we talked about a couple episodes ago. But the idea is we're going to always choose the job to serve next, which is closest to the current position of the read-write head. So if the read-write head starts at position 52, and this was the order that jobs arrived in, keep in mind that we can't serve jobs typically as fast as they arrive. Jobs are constantly arriving, on-demand paging, right? Where the disk, all of the parts of our address space are stored on disk. This matters. So our jobs arrive typically faster than we can serve them, so we get this queue building up. So we're not going to serve 104 next. We look at the jobs in the queue and we realize that job 65 is actually the closest to us, so we'll serve it first. And then 70, and then 37, and then 14, and then 104, and so on and so forth. So you can see that the head movement here is significantly reduced. Unfortunately, because jobs are constantly arriving, if all of those jobs are down here near track 50, this job out here, track 183, when does it get served? I don't know. I don't know when it gets served. Starves. So there is a way to do this that is fair and prevents starvation, and relative to first come, first serve, does minimize the seek time, or at least it reduces it. And it's called the elevator algorithm. It's also known as scan, and it's something, or a variant of this, is what any of your disks would actually be doing. Now what the idea is it's called elevator because it behaves like an elevator. If you get in the elevator on floor 17 and you want to go down, but everybody else in the elevator is going up, even if you want to go to floor 16, which is one below you, we don't go to floor 16 because it's the closest. We were going up. And so we will continue to go up and serve all of those customers in the elevator that wanted to go up. And once we reach the top, we're going to turn around and go back down. So this is what elevator does. It starts at some position, it chooses a direction to go, and then it's going to serve every job it sees as it travels towards that edge of the disk. When it gets either to there's no more jobs in front of it, or it's at the edge of the disk, the head is going to turn around and go back the other way and will serve all the jobs that we see on the way back. So we're going to bounce back and forth from one side of the disk to the other. Now, what's interesting is that this doesn't have any starvation, because if you leave a track and keep moving this way and a job appears right here just after you've left, that job won't starve, because all you have to do is you're going to go to the end of the disk, that last job, you're going to turn around and you're going to come back. And then you're going to go back and back and back and forth. So you hit the edge and then you come back. So that's the elevator algorithm. It's fairly straightforward. All right. Now, before we get into talking about the device registers for our disks, I'd like to show you a sample problem. Now, we're not going to take this sample problem up today. We'll take it up in episode number 19. So this is disk I/O that is in that sample problem package that's posted to Piazza. It has 2 parts. And what we have in this sample problem, I guess you can't see it there because of the text. There we go. Is we have a sample disk drive and we have a program that is going to do some computation and then do an I/O operation. And what we want to know is, what is the CPU utilization for this program that does 5 milliseconds of compute followed by an I/O operation, and it repeats. And we try to estimate the CPU utilization when we have 1 process, and we estimate the CPU utilization when we have 2 processes. So take a few minutes at home over the next few days and see if you can solve this problem. Now, if you're not familiar with the concept of CPU utilization, remember this. When the I/O operation is happening, the CPU is not being used, because the CPU does not control the rotational latency. It does not control moving the seek or anything like that. So the CPU is idle while our I/O request is actually happening. And we want to know what percentage of the CPU time is it idle, that is not doing anything. And the other thing I want to keep in your mind is that you can't have 2 I/O operations happening at the same time, because the read-write heads move together as one. They don't move separately. So you can only do 1 I/O operation at a time. My recommendation for this problem is compute how long it takes to do a service request on this drive. And once you've figured that out, do kind of that timeline approach that we did from one of our very first sample problems. All right, so going back then, let's now take a look at our disk controller. And it has 5, in OS 161 that is, it has 5 device registers. We have a status register, which tells us how many sectors our disk has. And we also have a status and command register, which tells us what the disk is doing right now. And so it tells us what is the disk doing, but when we write to this, we are telling the disk what we want to do. Then we have a command register, and the command register is responsible for when you write a sector number to it, that will actually cause the disk to either read or write depending on what you have done. So for example, how you would do this is into the sector number register, you would write, say, into the status register, you write, I want to write. And then once you write sector 57 to the sector number, the disk would then perform a write. Then we have another status register for the rotational speed, and you can imagine this is used in estimating how long an operation is going to take. And then we have a very large device register, which is the size of an entire sector. It's 512 bytes, and that is our transfer buffer. So if we are writing to the disk, we will put 512 bytes of data into the transfer buffer. And if we are reading, the disk will put 512 bytes in here that we are responsible for reading from. So this is either where we put data to go onto the disk or we read data to get it off of the disk. All right. So let's look at how we would write to this disk and read to this disk by implementing the device driver. So first off, we've made the two observations. Number one, you can only do sector-based reads and writes on a disk. And number two, you can only do one read or write at a time on a disk. Disks do not support multiple reads or multiple writes or reads and writes at the same time. One at a time, single file. So we need to offer some synchronization in our device driver to make sure that only one I/O operation is happening at a time. So we'll introduce a semaphore called the disk semaphore that's going to protect our lovely little disk. Then to write to the disk, we first put our data into the transfer buffer. Remember, that's an entire sector. Whether or not we want to use the entire sector, it doesn't matter. It's going to write the entire sector either way. So we put the data into the transfer buffer. And then we are going to write the target sector number into the sector register, and then we will put write into that command disk register. The write will then begin. But you'll notice that we are going to P another semaphore. Now the disk semaphore is a binary semaphore. We're using it as a lock. Then we have this other semaphore down here, the disk completion semaphore. And this one we are using as a barrier, actually. So its initial value is actually 0. It has 0 resources. We want the thread that initiated the disk write to have to wait for the write to complete before the operation returns. This makes sense because if you are writing to a disk in your C program, and then after you've written to the disk once, you want to write to it again, or maybe do something with the data, you don't want to start doing that while the write is still happening. You actually need the operation to complete before you move on. But furthermore, what happens if there's an error with the write? What thread cares about the error? The thread that initiated the write. So we need a way for this thread to wait for the operation to complete so that it makes sense from our C program, but also if there's any errors, it would make sense for that thread to handle the errors. So we are going to P the barrier, which is this disk completion semaphore. We are going to wait for the operation to complete. When the disk fires the interrupt to say I'm done, we are going to write to the disk status register, which acknowledges completion. It's just clearing it. And then we V the barrier. So we're going to release the barrier, which wakes up this thread over here. And then we decided not to do any error checking, but we should have, but we're done, so we can V the semaphore. Okay. The reason why we use semaphores for device drivers is because the thread that initiates contact with the device is almost never the thread that is running when the interrupt comes, which means that we may need synchronization primitives that can be released by threads that don't own them. And a lock can only be released by its owner, which means that a lock doesn't make sense. So we use semaphores here. Now the read handler, it kind of makes a bit more sense as to why we have that second semaphore. So with the read, we again can only have one happening at a time, so we P the disk semaphore. And then we are going to write the target sector number and read. Now you'll notice we didn't do anything with the transfer buffer because we are requesting data from the disk. Then what we're going to do is we P the barrier. We're going to wait for the read to complete. Now we have to wait here because we are requesting data from the disk. And if I go back to my program and I try to use that data, it doesn't exist yet because the disk hasn't finished. So I must wait until the disk has finished its job. So I have the barrier semaphore. Once the interrupt has fired and I've acted completion and I've released the barrier, the next thing I need to do before I release my hold on the disk is I need to copy that data, that sector that was read, out of the transfer buffer and into the program's address space. And who better to do that than the program the thread that actually made the request. Once we're done that, and we might handle some errors as well, then we can finally release our hold on the semaphore. So for disks, we have and for devices, we tend to use semaphores. Now, do all device drivers need 2 semaphores? Do they all need a barrier? No. Our clock rarely needs a barrier. Not everything needs a barrier. But there are certain operations where it only makes sense for the caller to handle the acknowledgement and any errors, or there are certain operations where we do need to wait for an operation to complete. Those are the device drivers that a barrier makes sense for, but we don't need a barrier for all of them. All right then, that's our mechanical drives. So the quick question says on Twitch, is there a reason we are using semaphores and not locks here? The reason is that, we could use a lock for the disk semaphore because it's only ever acquired and released by that thread. But that's for this specific example. Maybe we're checking the device's status, checking for errors, and maybe there are some cases where we may have the disk semaphore being released by a different thread. But for these examples here, technically speaking, we could have the disk semaphore as a lock, but the barrier one, the fact that we need a barrier, which would be 2 threads, we can't use a lock there, remember, because locks can only be released by their owner. And typically speaking, as a result of the different operations that happen on a disk, we use semaphores because we have often many operations where the thread that releases the semaphore is not the one that acquired it. And locks wouldn't work, and so it's just kind of, I want to say, almost a universal practice to use semaphores here. Just be careful with them. It's not to say you can't use locks, it's just it would be a lot harder to use all locks. All right, so SSDs. These are solid-state drives. They've been around for a really, really long time, but they haven't really worked so great until probably the last 5 or so years. I actually bought my first SSD, I think it was maybe 2007, and maybe it was 2008. That SSD, the manufacturer had a 35% failure rating. I unfortunately had one of those failing disks. But how do they work? So first off, a solid-state drive doesn't have any mechanically moving parts. If you were to open it up, and I have one here, but I'm not opening it up for you because I use it. If you did open it up, however, there's no moving parts inside. It's just a bunch of chips on a board. It's using integrated circuits for storage instead of magnetic surfaces. Now, that gives us a variety of benefits. Number one, no moving parts means it's going to consume less power and it's going to produce less heat. No moving parts means that it's going to be less fragile. No moving parts means that you're probably going to be a lot faster. So there's a lot of advantages to using solid-state drives. There are some downsides too, though, and I'll talk about those in a minute. So there have actually been a variety of implementation of solid-state drives over the years, and there's still more coming. One of the older methods is called DRAM, and DRAM, it was kind of like the RAM out of your computer, except it had a power source to keep the value. So actually how it was implemented is they had capacitors with the circuitry, and a capacitor, if you're not familiar, it can store a small charge for a small period of time. So the idea was that you would have these capacitors throughout the memory, and the capacitors would have a small amount of power for a short period of time so that the memory would actually keep the values stored in it. And then if the SSD was actually plugged into a computer that was on, those capacitors get periodically refreshed because the charge doesn't last very long in them, so they have to be periodically refreshed. So if the SSD was actually plugged into a computer that's on, the refresh comes from the main power supply. And if the computer was off, the DRAM style SSD actually has an onboard battery which performs the refresh of the capacitors to make sure that the storage is persistent. Well, that of course raises the question, what happens if the battery dies? Oops. By the way, so my very first computer, the date on the clock, there was actually like a battery, a watch battery on a lot of computers, older computers, and I haven't, like, I've got a big machine here and I haven't seen a watch battery on it actually, so I'm assuming they're using some different mechanism to do the clock. But on older computers, the clock on the motherboard was actually stored DRAM style. And what I mean by that is, in order to make sure that the computer was able to keep the time while it was off, so that when you turn it back on, it still had the correct date, it actually had a battery on the motherboard used to keep the clock with power, like used to cycle the capacitors there. And then what would happen is, one day you would turn your computer on and it would be January 1st, 1981 all over again. My clock battery was dead for a very long time. I never bothered to replace it. My clock battery was also 6 AA batteries, though, because it was really old. And this happened even in the 90s and the early 2000s, is these batteries for the clock would go dead and you actually had to open your computer up and replace the battery in your computer. I haven't had to do that for 15, 20 years though. It's a fun story. So DRAM is one way that we can do it, but most SSDs these days are using flash memory, which is also known as NAND flash memory because it is made up of a bunch of NAND gates. And I don't know much about electronics. You don't need to know anything about electronics for this course either, but they say that it traps electrons in a quantum cage. I don't know what that means. My understanding, however, is even flash drives can lose their stored electrons over time. And I think it's something like after 10 or 15 years, if those SSDs have not been plugged into a power source, in those 10 or 15 years, they may start to lose their charge and you may start to lose data. I have some USB keys from 10 years ago, but I'll be honest with you, I either throw them out or I use them still. So it's one of those things where if you have a disk sitting on a shelf for 10 years, I almost want to say, who cares? All right, so how does data get stored? So what we're going to do is, inside of this storage, we're actually going to treat it kind of like RAM. We're going to subdivide the memory into blocks and pages. Pages are going to be comparable in size to pages of virtual memory. So if you're using 4 kilobyte pages for virtual memory, then your SSD will probably also use 4 kilobyte pages. Why would we do that? On-demand paging, because when we want a page of the address space, it would be really nice if it was one I/O request. So make the pages on your disk the same as the size of pages of memory. And then pages are actually grouped together into blocks. Now pages tend to be either 2, 4, or 8 kilobytes, and that doesn't change too much, although it does depend on the operating system you're using. Block size, on the other hand, does tend to be getting bigger and bigger. Now, reads and writes, like on a traditional drive, reads and writes happen on a sector level. Well, we don't have sectors on an SSD, we have pages. Reads and writes happen at a page level, so we are doing page-based addressing. But there's a trick to this. This is where SSDs kind of get interesting. So first off, when we think of data as being empty, we think of it as being all zeros. And on an SSD, that's not true. An empty page is not all zeros, an empty page is all ones, because it's very cheap to transition from a 1 to a 0. So you can do writes of a page at a page level if the page has never been written to. But if you want to overwrite a page that has already been written, it is actually very difficult to transition from a 0 to a 1. And in order to do that transition, you actually need to apply a very high voltage. And unfortunately, SSDs cannot give that high voltage at a page level. They can only provide that high voltage to a block. So you can do page level reading, that's not a problem. And if you are writing a brand new page, you can write at a page level. But if you want to overwrite or delete a page, you can't do it at the page level, you can only do it at a block level. Because we can only apply the high voltage to go from 0 to 1 at a block level. And that means that when we are overwriting pages of our SSD, we actually need to talk about some algorithms for doing that. So there's the naive solution, which is the old way of doing things. It's not to say we don't still use it. And what it does is it says when you need to overwrite a page of memory on an SSD, and since we can't overwrite the individual page, we will instead read the entire block that contains that page into RAM. So instead of writing 4 kilobytes, we now have to read 32 or more megabytes from the disk into memory. We perform the modification to the block in memory, and then we will write the entire block back to the SSD. So it's naive because it's slow, but it works. It does actually work. It's very easy to do. Now your SSD is smarter than that, though. SSDs have fairly complicated controllers, and they have a sneaky little way of doing writes without having to use the naive solution for every time you overwrite something. What they're going to do is they keep track of every page that is in use and every page that hasn't been used. So they keep track of all of the pages that are currently in use, all of the pages that haven't been touched, and all of the pages which are garbage. Nobody's using them, but they're also not all ones. What they're going to do is when you say, hey, I want to delete or overwrite this page, they're going to be like, oh, okay. Well, I don't want to do a block-based read-write, so I'm going to find you an unused page. So it goes through its table and it finds a page that isn't in use, and it's all ones, and it's going to write your page to that page. And then it's going to update its translation table to say, this page of the file now lives on this page of the disk. And then we mark the old page as invalid, as in it's not in use and it hasn't been cleaned either. And then periodically, as your disk runs out of free clean pages, we actually have to do some garbage collection where we actually reset those garbage pages back to ones. So that's kind of a fun little thing that SSDs can do to improve the writes. Now, we do consider on an SSD sequential and random I/O to be the same cost. And the reason is we don't have any moving parts. My understanding is there is a teeny tiny difference between sequential versus random I/O, but it's not something that's really worth discussing or doing any calculations for. It's not a noticeable difference. A couple other interesting things about SSDs to talk about is SSDs actually have a limited lifespan. Even if you keep it plugged into your computer, they only last so long. And that's because you can only apply that voltage to the page so many times before it just won't flip the bit. It just won't do it. So they say that SSDs, each cell has a limited number of write cycles before the cells become read-only. And you might be thinking it's got to be millions or billions of writes that can happen per cell before it becomes read-only. I don't want to frighten you, but it's actually only about 100,000. So your SSD controller, aside from doing a bunch of other very clever things, also prefers random I/O to sequential I/O because it doesn't want to prematurely wear down one part of the disk before others. It would actually like the whole disk to wear down at the same time or at the same rate. So your SSD actually does something called wear leveling to make sure that writes are kind of happening uniformly across the disk, and that way everything kind of wears out at the same time. What's really interesting is depending on how much money you spend on the SSD, there are bad ones and there are good ones. A really cheap bad SSD controller, after about 5% of the disk becomes read-only, the controller may actually mark the whole disk as read-only. Whereas a higher quality controller may take a significantly higher percentage of the disk to be marked as read-only before it says, you know what, this disk is all read-only. So that's some other interesting facts. Now, on that note, a lot of people may have grown up with this idea, I need to defrag my files. I don't know what I'm doing, but I need to defrag. And you know, when I was a kid, I had to defrag my files. So this is one of those things where if you've grown up with mechanical drives, you may be very accustomed to doing periodically, running a defrag. Don't defrag an SSD. Number one, there's no reason, because there's no advantage of sequential versus random I/O to us. But also because you're breaking the concept of wear leveling and you're performing unnecessary writes to something that has a very limited number of supported writes. But what is defrag? So what defrag is we actually store files kind of like we do address spaces, where we have the pages of the address space just kind of scattered to the wind in RAM. Well, we do the same with our files. We divide our files into a bunch of pages and then we scatter them across the disk so that each allocation on the disk is the same size, so we have no so that we don't have to find a contiguous block. The problem, of course, is that means that our disk ends up looking like a scattered mess of a bunch of files jumbled together. And if this was a mechanical drive, that would mean we are doing random I/O all the time, which, as we know now, random I/O is very, very slow compared to sequential I/O. So in the 80s and 90s and early 2000s, when we were really using these older, slower mechanical drives, you had to periodically run a program called defrag. And what defrag would do was it would take all of the blocks of your files and try to make them sequential on the disk to improve the sequential I/O. So make it so there was more sequential I/O operations than non-sequential. And in the 90s, I think I had to run this almost every other day, and it did have a noticeable impact on my disk's performance. But on an SSD, it doesn't do anything. If anything, defragging does more damage than good. So please don't run that on your SSD. One other interesting fact about SSDs is that if they go down, so if you have a mechanical hard drive and it breaks, you can pay somebody to get the data off of it. I have heard that it takes 7 overwrites in order to truly erase something. So if you actually try to delete something on your disk, there's this thing called secure delete versus just a regular delete. You have to do that 7 times before you can be guaranteed that it is wiped from a mechanical drive. Mechanical drives are actually really good at kind of keeping echoes of what data was there. So even if your mechanical drive fails, you can take it to someone and for a few $100 they can almost always recover most of your data from it. And this actually gets governments in trouble because their IT department just thinks, oh, I'll just toss the old disk out in the bin out back. And then, dumpster divers come along and they grab a bunch of the health ministry's disks, and now we have health records out in the public because they forgot to properly scrub the disks. You want to know how do you effectively dispose of mechanical hard drives? You smash them. You smash them to smithereens. And it's good for getting out frustration too, right? Everybody's frustrated. All right. But on an SSD, if they break, the chances that you can recover data are really low. So my first SSD, the controller actually broke on it, and 100% of my data was gone. There was nothing I could do. There's nobody I could pay. I can't replace the controller component to get my data back. It was gone. So that's a fun part about SSDs. In general, though, SSDs, they're faster, they're more reliable, they use less power. So they are a good thing, but they are not without their faults. Now, one last thing I want to talk about is this concept of persistent RAM, which is something that is really coming up to the forefront. Like, we're starting to see this as something we can buy in the marketplace. So the idea is we want RAM where the values persist. Now, the performance of persistent RAM is it's roughly an SSD's performance, maybe a little bit better. It's not quite your physical memory's speed yet, but it is getting better. And there's a few different names. There's ReRAM or 3D X-Point, Intel Optane. There's a few different ones. But the idea that we have for this, why do we want persistent RAM? It's not so useful for you, a home user, because you can just buy an SSD and it's cheaper and you're not going to see any big benefits. But where we see benefits for persistent memory is we want to have a cache that persists. And it's not so important for programs running because they don't tend to cache a significant amount of important data, but it's important for caching data from secondary storage, so from mechanical hard drives. So let's say that you're working with a bunch of big films that are living on a bunch of mechanical disks. You want to be able to cache data blocks from that film and have that cache kept such that the next time you turn your computer on, you still have that cache. You want to make sure that data from slower storage devices, which are much bigger, can be cached in a persistent way across power cycles. So we actually use this persistent memory, this persistent RAM, to store things like inodes and data blocks from files across power cycles. And it really improves the speed for I/O operations. And I know some of these terms may not make sense to you right now. They will soon. And we will revisit that shortly. So yeah, that's a cool thing that people are using. And again, this is not really for consumers. This is really meant for things like data centers, things like Amazon. They're going to be interested in persistent memory because it gives them abilities to cache large amounts of data in faster memory without having to buy large SSDs for that. They can just use these caches for that. Well, that's kind of neat. All right, now with that, that is actually the end of our devices section. It's actually a fairly small section of the course. On our next episode, we're actually going to start the file systems. And I have to look at the schedule because our next episode might actually be how to do assignment 3. I'll let you know. Either way, next episode next week will either be looking at file systems or assignment 3. So I will see you next week, and I hope you have a lovely weekend.
Good evening, Mr. Dillinger.
Thank you, Peter. You can go now.
Yes, sir.
Thank you, Peter. You can go.
Hello, Mr. Dillinger. Thanks for coming back early.
No problem, Master C. If you've seen one consumer electronics show, you've seen them all. What's up?
It's your friend, the boy detective. He's nosing around again.
Flynn?
Yes? It felt like Flint.
Still looking for that old file. Can't you just appropriate it?
I have. I put it in my memory, which he hasn't located.
But he might find it.
I'm afraid so. I spotted him this time and kept him out. He's getting trickier all the time.
I think we should shut down all access until we find that Flynn, just to be safe.
There's a 68.71% chance you're right.
Cute.